Hello everyone, and welcome to today's presentation. I'm excited to talk with you about tertiary wastewater treatment. On this first slide, you'll see the title, Tertiary Wastewater Treatment, and a brief overview. Over the course of this presentation, we'll explore how advanced treatment processes go beyond basic methods to remove specific pollutants. We'll cover key topics like phosphorus removal, nitrification and denitrification, and innovative approaches such as constructed wetlands. I'm looking forward to sharing insights on how these processes help protect our environment and improve water quality. Let's get started. Today, I'll be giving an overview of constructed wetlands. These systems are designed to treat wastewater on a small scale by mimicking what natural wetlands do in the environment. Their main goal is to remove nitrogen from waste streams, which is a key part of improving water quality. But they also provide other treatment benefits, making them quite versatile. The beauty of these engineered systems is that they closely resemble natural wetlands, relying on biological processes. Essentially, they harness the relationship between aquatic plants, like bulrushes and cattails, and microorganisms. This partnership is what allows the system to process pollutants effectively. Now, let's talk about the key components. These wetlands incorporate specific plants that naturally uptake nutrients from the wastewater. These plants, such as bulrushes and cattails, play a vital role. They work together with colonies of microorganisms to convert nitrogen compounds through processes called nitrification and denitrification. This creates a living, breathing treatment system that uses natural biological mechanisms to clean the water. So, in essence, constructed wetlands are an eco-friendly, efficient way to treat wastewater by mimicking the natural processes found in wetlands, focusing on nitrogen removal, and utilizing the symbiosis between plants and microorganisms. Let's dive into the theory of operation behind constructed wetlands. Essentially, these systems use wetland plants to absorb nutrients from wastewater. The core idea combines microbiological growth with the natural metabolism of aquatic plants to facilitate processes like nitrification and denitrification, which are crucial for removing nitrogen compounds. When selecting plants, species such as bulrushes and cattails are popular because they are highly effective at taking up nutrients and also help transfer oxygen, which supports the microbial activity necessary for treatment. Now, there are two main types of constructed wetlands we should understand: subsurface flow systems and overland flow systems. Subsurface flow systems, sometimes called reed beds, distribute wastewater through underground pipe networks within beds filled with gravel or pumice. This setup is similar to trickling filters, encouraging the growth of microbiological colonies that help break down pollutants. On the other hand, overland flow systems allow the wastewater to surface, where it can be exposed to sunlight and aeration from the wind. This surface application not only prevents media clogging, but also mimics natural wetlands more closely. Both approaches leverage natural processes to effectively treat wastewater, aligning with our overall goal of sustainable and ecologically friendly treatment methods. Let's talk about subsurface flow wetlands, specifically their design and some of the challenges they face. These systems work by distributing wastewater through pipe networks located beneath the surface, typically within beds of gravel or pumice. They operate in a manner similar to trickling filters, where microbiological colonies develop to help remove nutrients from the water. You'll often find these units paired with septic tanks, which are designed to remove settleable solids that could clog the media and cause water to surface prematurely. Now, one of the critical issues with these systems is that many lack effective methods for removing larger objects that are common in wastewater. Grit removal, for example, is a significant problem because accumulated grit can reduce the detention time in septic tanks, which impacts overall treatment efficiency. Plus, the suspended solids coming from septic tanks, combined with the media's limited ability to slew off solids, unlike trickling filters, can lead to plugging of the media. When this happens, wastewater is forced to surface, creating operational issues. The beds themselves are typically planted with bulrushes and cattails. These plants are not just for nutrient removal, they're also meant to supply oxygen to the subsurface media, helping prevent septic conditions and odors. However, there's a catch. When the water turns septic in the septic tank and suspended solids leave the tank, the high oxygen demand from the resulting water can overwhelm the system. This often results in oxygen being forced to the surface, where odors develop. Research supports these challenges. For instance, in W. Daniel Boyven's study on constructed wetlands in New Mexico, it was found that subsurface flow wetlands are unable to effectively remove nitrogen from septic tank effluent to meet the water quality standards. The main issue here is the need for additional oxygen to facilitate nitrification, which these systems simply can't provide under current designs. So overall, while subsurface flow wetlands are a promising technology, there are significant design and operational challenges that need attention to improve their effectiveness. Let's take a closer look at the gap between the maintenance expectations set by marketing claims and the reality of operating constructed wetlands. Many promotional materials highlight the idea that these systems are set it and forget it, suggesting they require very little ongoing effort. This has been one of the major selling points, making them attractive for various projects. However, in actual practice, maintenance still plays a crucial role, even if the goal is minimal. For example, annually removing vegetative growth is essential to keep the system healthy and functioning properly. Think of this vegetative growth as the sludge that needs to be managed to prevent clogging or reduced performance. Additionally, many systems actually require mechanical aeration to maintain oxygen levels, which adds not only to operational complexity, but also to electrical and maintenance costs that were often underestimated or overlooked during the initial planning stages. So, while the marketing paints a picture of low-maintenance systems, the reality is that some level of active upkeep is necessary to keep these wetlands performing effectively over time. Understanding this helps us set more realistic expectations and plan appropriately for long-term success. Now, let's look at overland flow wetlands, which are an alternative approach used not only throughout New Mexico, but in many other regions as well. These constructed wetlands utilize surface flows, meaning the wastewater flows over the surface of the media. One of the main benefits of this method is that it prevents media clogging, which is a common issue in subsurface flow systems. Plus, because the water is visible on the surface, it allows for easier observation and maintenance of the system. Another important aspect is lagoon integration. These systems often incorporate lagoon-type components, which help increase oxygen levels and promote natural treatment processes like algae growth and wind action. This combination can enhance overall treatment efficiency. However, there are ongoing challenges to consider. Odor problems can still persist, especially since the system naturally produces swamp gases similar to those in natural wetlands. Managing BOD, or biochemical oxygen demand, from septic tanks can also be tricky. I should emphasize that this requires careful management to prevent overloading. Additionally, debris removal is essential to keep the system functioning properly, and mosquito control is another critical aspect. Sometimes, adding gambusia fish, which eat mosquito larvae, can be a helpful strategy. While this overland flow design addresses some issues seen in subsurface systems, it's important to recognize that odor issues and BOD loading from septic tanks remain significant challenges. So, ongoing maintenance and management are key to ensuring these wetlands function effectively and sustainably. Let's talk about the effective uses of constructed wetlands. The most successful operations are typically implemented at the end of conventional treatment processes, such as activated sludge or lagoon systems. In this setup, the wetland functions more as a polishing step rather than the primary treatment. The filtering action provided by the media and the plant growth has proven to be quite effective for filtering out total suspended solids, or TSS, and non-soluble BOD in the treated wastewater effluents. However, there are some limitations and performance issues to keep in mind. The very filtering action that helps improve water quality can also lead to clogging over time, which means wetlands require periodic maintenance and media replacement. When it comes to nitrogen removal, the results haven't been as successful as initially hoped. Many of the data reports on wetlands have been sporadic and inconsistent, which makes it difficult to predict their performance reliably. Looking at long-term research, studies like those by Dr. Michael Richard in Colorado show that wetlands can periodically purge nitrogen and phosphorus. This indicates that these nutrients are not permanently removed, but are instead temporarily stored and later released back into the environment. Understanding these dynamics is crucial as we consider the role of wetlands in integrated treatment systems and their overall effectiveness. Now, let's talk about wetlands operations and maintenance. While operators don't have full control over how the wetland functions, there are several key maintenance activities that are essential to keep everything running smoothly and to prevent system failures. First, dike and vegetation management play a crucial role. We need to maintain the dikes by keeping low-growing grass on them, which helps prevent erosion. Regularly cutting the grass and properly disposing of the clippings is important. We also want to discourage burrowing animals that are attracted to lush vegetation, as they can compromise the integrity of the dikes. Next, daily housekeeping is vital. This helps control odors, insects, and rodents. Every day, we should remove screenings and grit from pretreatment areas and dispose of them properly. Keeping the facility neat and clean by preventing trash buildup is also a key part of daily maintenance. Moving on to seasonal vegetation removal. At the end of the growing season, we need to remove excess wetland vegetation. Burning can be an option, but it requires careful precautions. We must protect the wetland lining and any exposed plastic pipes by covering them with wet burlap and buckets before burning. It's also important to obtain the necessary permits, ensure there's enough water supply, and have adequate manpower ready. Finally, there are alternative methods for vegetation management, such as cutting instead of burning. If we choose to cut, it's important to remove and dispose of the cuttings properly, following local regulations and facility requirements. All these maintenance activities are interconnected and vital for the overall health and functionality of the wetland system, helping us achieve the environmental goals we're aiming for. Now let's talk about process control testing and record keeping. For wetland systems, it's essential to have a comprehensive testing program in place. Key parameters to monitor include pH, temperature, dissolved oxygen, and nitrate levels. These tests should be conducted at least twice a week for effluent, specifically measuring dew, pH, and temperature. Based on the results, adjusting flow patterns can help maintain a minimum effluent dissolved oxygen level of 0.5 milligrams per liter, which is crucial for system health. When it comes to nitrogen, sampling must include both influent and effluent for total nitrogen, and additionally, effluent testing for nitrate nitrogen. Ideally, nitrogen testing should be done weekly, or at the very least monthly, to keep a close eye on nitrogen removal efficiency. Accurate flow measurements are also vital, using totalized flow data, so we can interpret the test results meaningfully. Remember, flow measurements need to be taken at both the influent and effluent points to ensure accuracy. Moving on to record keeping, maintaining detailed records of flow data and process control tests is critical for proper operation and maintenance. Operators should also keep copies of all as-built drawings and permit testing documentation. Daily records of temperature and weather conditions can be incredibly helpful when troubleshooting system issues. These records serve multiple purposes. They help ensure regulatory compliance, track system performance over time, guide troubleshooting efforts, and document operational decisions. When records are well maintained, they enable us to identify trends, anticipate problems before they escalate, and optimize system performance for long-term success. Let's talk about phosphorus removal and why it's an environmental necessity. Phosphorus is a critical nutrient for algae. It essentially acts as a food source. When phosphorus combines with inorganic nitrogen, it creates a recipe for serious pollution problems in our water bodies. This is because together, these nutrients promote excessive algae growth. Algae in water might seem harmless at first, but they can be quite unsightly and often cause unpleasant tastes and odors in drinking water supplies. More concerning is what happens when algae die and decay. This process can lead to severe oxygen depletion in streams and lakes, which can be devastating, killing fish and other aquatic wildlife. Now, when treatment plants discharge phosphorus into receiving waters, it adds to this problem. The combination of phosphorus and nitrogen fuels those massive algae blooms we're all familiar with. These blooms, besides being unsightly and smelly, can cause serious oxygen depletion when the algae die off and decay, leading to the death of aquatic life. This is why removal becomes so important. The EPA mandates phosphorus removal to protect water quality. By removing phosphorus from wastewater effluent, we reduce one of the essential nutrients that algae need to grow. This significantly lowers the potential for algae blooms in lakes and rivers receiving this discharge. Both the EPA and other water quality agencies recognize this need. They require wastewater treatment plants to remove phosphorus as a key step in safeguarding our water bodies from excessive algae growths. So, in essence, phosphorus removal isn't just about compliance. It's about preserving healthy, balanced ecosystems and ensuring clean, safe water for everyone. Let's now take a look at the main methods used for phosphorus removal, which are crucial for maintaining water quality. There are 3 primary techniques: lime precipitation, luxury uptake, and filtration after aluminum sulfate flocculation. Each method relies on different principles, but ultimately aims to reduce phosphorus levels in the treated effluent. Starting with lime precipitation, this process involves adding calcium hydroxide, or lime, to the wastewater. When mixed at the right concentration, it raises the pH and causes a chemical reaction where phosphorus, calcium, and hydroxide ions combine. This forms a compound that flocculates into heavier solids, which then settle out in a clarifier. Additionally, lime reacts with alkalinity in the water to produce calcium carbonate, which settles along with the phosphorus sludge. The process involves steps like coagulation to break apart particles, flocculation to gather suspended solids, and sedimentation to allow gravity to do its work. Equipment needed includes lime feeders, mixing tanks, chemical clarifiers, pumps, pH adjustment systems, and facilities for sludge handling. Next, we have luxury uptake, a fascinating biological approach. Here, activated sludge bacteria are moved into an anaerobic or oxygen-free environment. Under these conditions, the bacteria perceive an emergency and release phosphorus from their cells into the water. Then, lime is used to settle the phosphorus out. After this, the bacteria are returned to oxygen-rich zones with food, where they immediately take up phosphorus again. This is what we call the luxury uptake. To implement this method, you need standard activated sludge units plus a deep basin for anaerobic conditions, along with a lime clarification tank to remove the phosphorus. Operators must carefully control the detention times, long enough for phosphorus release, but not so long that bacteria die. The bacteria are then returned to the aeration tanks for revival and continued phosphorus removal. Finally, let's discuss aluminum sulfate, or alum, flocculation. Alum reacts with alkalinity in the wastewater to produce aluminum hydroxide floc. These aluminum phosphate particles attach to each other, becoming heavy enough to settle in a clarifier. The removal process involves forming insoluble complexes that trap phosphorus. Because alum floc can be slow to settle, a filter, like a sand or mixed media filter, is often employed afterward to catch remaining floc particles. To control this process, alum dosage is often automated based on pH readings, with pH control being critical for optimal removal. Typical alum dosages range from 200 to 400 milligrams per liter, aiming to bring phosphorus levels down to very low concentrations. Currently, there are no cost-effective ways to recover alum, so it's used as a chemical additive without recovery options. In summary, these methods, chemical, biological, and combined chemical-biological, are all vital tools in our arsenal to meet water quality standards by effectively removing phosphorus. Let's wrap up with a summary of tertiary treatment excellence. First, when it comes to constructed wetlands, they are most effective as a polishing process after conventional treatment. However, Subsurface flow systems often face issues like plugging and high oxygen demand, which can limit their effectiveness. Overland flow systems tend to better mimic natural wetlands and are generally more resilient, but they still require significant maintenance despite some marketing claims suggesting they are maintenance-free. Performance in nitrogen removal can be inconsistent and sporadic, so careful monitoring is essential. Now, moving on to phosphorus removal, this step is crucial for preventing algae blooms and protecting aquatic ecosystems. One cost-effective method is lime precipitation, which requires pH adjustment and lime recovery. There's also luxury uptake, a biological process that can be very effective but needs precise operational control to work well. Alum flocculation is another option. It's effective, but tends to be more expensive and requires filtration to remove the floc. The key point is that all these methods can meet regulatory requirements, but only if they are properly operated. Successful tertiary treatment depends on comprehensive process control, thorough testing, meticulous record keeping, regular maintenance, and skilled operators who truly understand the complex biological and chemical processes involved. Whether we're using constructed wetlands for polishing or chemical and biological methods for phosphorus removal, proper operation is what ultimately protects our receiving waters and aquatic ecosystems while helping us meet ever more stringent regulations.